Welcome again. In this presentation, we will check the performance of the pole placement controller. We will design the controller, simulate the closed loop, we will find that we have to re-specify, and then we will assess the performance of the new controller. We will present Scilab code and results in this presentation. Let us recall the good and bad portions of the plant. I want you to remember that we have bad 0 here and we expect some poor performance because of this. We also have k equals 1. We obtained the closed loop characteristic polynomial as given here, and we want to solve the following Aryabhata's identity. And so let me substitute. AB is given here, which is the second line here. So I write it here, the unknown is R1. From the second term I have z power minus 1. For BB I have this into S1, another unknown, equals phi CL, which is this. Let me write that. Let me solve using Aryabhata's identity solver, and it is called xdyn c dot SCI. You have already seen this. We get S1 as given here and R1 as a first degree polynomial. Here is the code that I have used, ball underscore basic dot SCE. It uses my C2D. It makes use of a function called desired and a function called pp underscore basic. I am going to show these two functions subsequently. Here is the function desired.sci. You can see that I calculate nr, phi, omega, epsilon and so on. And then the other important function pp underscore basic, which splits the polynomial a into good and bad, similarly for b and so on. And then it calls xdync function and gets S1 R1. After you compute it, you initialize it using this file whose name is given here, that loads this xcos file called basic.xcos. The word basic is the same thing that I have used in the MATLAB file. There it was basic.mdl. I have tried to use the same name as far as possible. Of course the type is different, here it is xcos, there it is mdl. I invoke this. The moment it is invoked, it loads it, imports it and also simulates. You do not have to press any button, you get the result. So here is the basic.xcos screenshot. It is possible to simulate it using state space also. Remember in the previous slide, I have the plant given in terms of numerator and denominator transfer functions. Here I have given it in terms of state space. If you want to use this, you would invoke the second parameter file, ball basic underscore param underscore 2.sce. It invokes this other xcos file which is given by c underscore ss underscore cl. Once again, this is simulated, loaded and simulated. It does not matter which one you use, you get the same results which I show in the next slide. This is the plant output. Here is the corresponding controller effort. Both are presented here. Now let us assess the controller performance. You can see that the overshoot and the settling time constraints have been met. Overshoot is of the order of 0.05, it is 1/4 of this distance, so that is okay. Settling time constraint is also met. You see that it settles at about 0.5, which was the other requirement. But notice that the auxiliary condition on rise time is not met, here it is of the order of 0.225, whereas we actually wanted it to be 0.15. So what we obtained here is about 1.5 times what we wanted. What is the reason? Why did this not happen? There could be many reasons. One of them is the bad zero. There could be other reasons as well. In fact, I would want you to find out at least one other reason why we are not getting the same performance. But what we will do is, instead of going into those details, we will see if we can come up with an engineering approach to address this problem. Notice that I wanted 0.15 and I got 0.225 as the rise time. That is, we obtained 1.5 times what we wanted. So we back calculate and say that if I want 0.15, perhaps I should specify the rise time as 0.1. So if we get 1.5 times that, we will get 0.15. So let us try reducing the required rise time. So these are the values that we had earlier, the good and bad factors and also k. And when I invoke the rise time condition to be 0.1 second, I get these epsilon, rho, omega values. Recall that previously we obtained a larger rho value. The new rho value is closer to the origin. As a result, the system is faster. The frequency is also faster compared to this. So once again the system is faster, and by requiring rise time to be smaller, we wanted the system to be faster, and that is indirectly achieved through rho and omega. For this rho and omega, I get the corresponding phi CL as given here. Then I solve the Aryabhata's identity. I get R1 and S1 as given here. Now let me go back and just simulate as we did before. This is the output we get with the rise time as 0.1 second. You can see that now the rise time condition also is met. The actual value is 1.5 times what we wanted here. As a matter of fact, this is at 0.15. So our choice was okay. Here is the input for the same situation. So now we see that all the requirements have been met. This is the plant output, this is the plant input, controller effort, and the overshoot condition is met. It also settles, in fact, a lot earlier, about 3 times this. We compare the plant output that we obtained previously to the one we obtained just now. It is faster and all other conditions are also better. Overshoot is about the same, it settles faster as compared to here. Is there a trade-off? So let us compare the control effort we obtained earlier with a new one. You can see the new controller requires a larger control effort at the beginning. Here it is smaller previously. At the higher level it is about the same, there is not too much difference. With this we have come to the end of this presentation. Let us recall what we did. We implemented the controller using the specifications that we obtained earlier, and we found the controller did not meet our requirements. So what we did was we made an engineering approximation. We expected a particular kind of tuning to work. We made the system little faster, and we found the new controller met our requirements. So as an engineer, you are expected to do this kind of tuning. We will see more examples in subsequent videos. Goodbye.